Well, friends, we make a big turn today. We make a very, very big turn, and we talk about what's called the area function. That is to say, we're going to talk about a function that's going to keep track of area under a different function. And I'll show you what I mean. Let's pretend, just for argument's sake, 1, 2, 3, -1. Let's pretend that we are graphing over here the function f of x is 2. And let's pretend that over here, 1, 2, 3, -1, over here we have some function capital F of x. And capital F of x is going to keep track of the signed area under little f of x from 0 to x, which means, and I should have been way more careful with this than I was, that we're going to use a dummy variable here, f of t dt. Now go ahead and ask why. Go ahead. Okay, good question. When this x changes, but this stays as is. In other words, this is the red function. This is the red function. And the fact that this is the red function does not change at all throughout the problem. But when this x changes, this x changes. So that when I find f of 0, capital F of 0 is the integral from 0 to 0 of f of t dt. Well, I think we know what that is. That's 0. That's 0. And when I find capital F of 1, that is the integral from 0 to 1 of f of t dt. Well, the integral from 0 to 1, that's the integral from 0 to 1. That is a rectangle whose height is 2 and whose width is 1. This is a rectangle of area 2. Capital F of 1 is 2. Similarly, capital F of 2. Capital F of 2 would be the integral from 0 to 2. I think I know what that is. So that's 2, 4, and you can well imagine that this thing is a line. In fact, you can well imagine that capital F of x is 2x. You can well imagine what that is. Well, that's fine. Consider the following. What if I have some function? What if I have the function g of x is x? And I have some other function over here that says capital G of x is the integral from 1 to x of g of t dt. I mean, just for argument's sake. Just for argument's sake. Well, in that case, if I were looking for g of 1, that would be pretty easy. I got to put a scale on here at some point. Got to put a scale on there at some point. G of 1 is 0. That's not too bad. Here's 1. So when I go to look for g of 2, capital G of 2 is this area. And this area is the area of a trapezoid. That's 1/2 the height times the sum of the bases. And that's 3/2. That's 3/2. 3/2. And then I start thinking about what capital G of 0 is. Well, capital G of 0, here, I just gotta get rid of this. Capital G of 0 would be the area, I'll get rid of that, in here. capital G of 0 is the integral from 1 to 0 of g of t dt. Well, capital G of 0, that's this area. That's 1/2 base height. That's 1/2, but we're reading from right to left, and so that's a negative answer. And then when we take things to -1, if I want capital G of -1, that's the integral from 1 to -1. Well, guess what happens if we take the area from 1 to -1? This positive and that negative area cancel, and I'm right back to 0. And in fact, you get this crazy thing. So here's where things get just bizarre, just a little bit bizarre. When I had a nice constant, the area function gave me a line. And when I had a line, the area function gave me what appears to be a parabola. And now I'm starting to wonder if there's a connection. If there's a connection between this function and this function that's a little bit more than what we have already thought. And I've got to let you think about that for a while, and we'll talk about that when we get to class. But at least you will have seen this, and that's going to give you a head start on all the discussion that we're going to have. Okay, go get 'em, everybody.